We have, as you saw in that tutorial, two different flavors of plates. We have plates that are hooked to a battery and plates that are insulated or isolated, where we charge them up and then we take the battery away. Let's first of all look at these insulated plates. The charge is placed on the plate somehow, usually by a battery that we take away, but it's always negative on one and positive on the other. Now if we take those plates and move them closer together, the thing that stays the same is the charge density. It can't go anywhere, okay? It's stuck. Now the charge density is what creates the electric field. So I have to have the same electric field between those two sets of plates. Now, what's different is the voltage between the plates. The voltage is how much Verk I would have to do to take 1 coulomb from plate to plate. I would have to push the same amount between both plates, but here I would have to push further. If I look at the ED equation, the E field that I'm fighting is the same between both sets of plates, but the distance gets smaller. So that means the total voltage gets smaller. Now, here's an analogy. Remember, voltage is Verk. Verk I have to do to bring 1 coulomb across. But think of it as Verk. The university comes and they say, we can't afford to keep the buildings open for 17 weeks during a semester. So we are going to shorten each semester by 4 weeks. Okay? And we're going to do it in such a way, we told the professors, that they cannot require more work each week. Whatever assignments they were giving you per week, that has to stay the same. What does that tell you about the total amount of work that's going to get done during the semester?
Less.
It's going to be less. You're not going to cover all the chapters you used to cover. Okay? You're going to get cheated. Now, let's look at the case where there's a battery connected to the plates. I told you last day that if you hook a 6-volt battery to a pair of metal plates, the voltage between the plates has to be 6 volts. Let me show you how I know that. It doesn't matter which path I take from plate to plate. So let's take this path. Let's go up through the metal. What's the electric field in this metal? 0. And so that means I'm fighting no field. It costs me no Verk. I do not change my voltage. Now to get that 1 coulomb through the battery, I have to do 6 joules of Verk on it. And that's done chemically by the battery. That's what the battery does. And then we go through the metal again, and that costs me 0. And so that means that the total Verk to get it from point A to point B was 6 volts, or 6 joules for each coulomb. And that's the voltage regardless of which path I take. Now, if I take that set of plates and I push them closer together, because of that battery, the voltage has to stay 6 volts. Come heck or high water. Now what that means is that the electric field has to get bigger. Why? Because if the voltage has to stay the same, but the distance is getting smaller, the E has to compensate. Back with the analogy. The university comes and they say, we can't keep the buildings open for 17 weeks. We're going to shorten the semester by 4 weeks. However, we have instructed your professors to cover just as many chapters in the book as they used to. What does that mean? You're going to be busting your butt every week that the buildings are open to get just as much done as you did before. The total Verk is going to stay the same. Okay? Now, that electric field is caused by surface charge. It's directly proportional. All you do is you take the surface charge, divide by this number. So what does that mean? When I push these plates together, in order to keep the voltage 6 volts, what the battery does is it increases the surface charge density. What that means is it steals more electrons off of this plate and puts them onto this plate. If I took a little tiny flashlight bulb and put it in that line right there, as I was moving the plates together, that bulb would light up, okay, because electrons would be racing over there to increase the field. Now, as soon as I got it to its location and stopped the plates, the bulb would go out. When I moved the plates further apart, the electrons would go back and the bulb would light again. I could make a light accordion with this. Just whenever I was moving the plates, it would be on. Whenever I stopped to turn around, it would go off. See if your neighbor understood that. Okay? Now, let's make the connection between that and your tutorial homework. Let's start with example 5, with the insulated plates. In this example, we have a positive green plate and a negative purple plate. And we have 2 points labeled A and B. Now, in this example, we do a couple of races. The first race is with protons. We take 2 protons, we let one there, we put one there, and we let them go. And they race off to B. And we want to know which one's going fastest when it gets to B. The second race is with electrons. We put electrons by the negative plate, we let them go, and they race off towards the positive plate. And the question is, which one's going fastest when they get to the positive plate? Now we have this ED equation, and it's so beautiful and simple that it is commonly misused. When I write the voltage is equal to the electric field times the distance, I am being sloppy. What I want to do is put labels or indices here. The voltage from point A to point B is the electric field times the distance from point A to point B. The voltage difference from the negative plate to the positive plate is going to be the electric field times the distance from the negative plate to the positive plate. If you're careful with those labels, you will not make mistakes. Let's look at these 2 races. Let's race the protons. In order to speed up, you have to change your voltage. The more you change the voltage, the more you speed up. So, if I look at the proton race, I have a certain voltage difference that proton is accelerated through from A to B. It's given by E times the distance from A to B. Well, let's look at how those things change. The electric field is caused by the sigma. The sigma is stuck. The electric field is the same. And the distance from A to B is the same. But wait a minute, Greg, you said that the voltage between those plates is smaller. Listen to the words I said. The voltage between the plates, from the negative plate to the positive plate, gets smaller. But not the voltage from A to B. The voltage from A to B stays the same. Because the electric field is the same, the distance from A to B is the same. The proton race is a tie. Now if I look at the electron race, well, it turns out that because the distance between the plates gets smaller, while the electric field stays the same, the voltage between these plates would be smaller than the voltage between these plates. If I let electrons go here and here, this one would be going fastest right before it hit the plate. Okay? Now, folks, how does that change the problem? If I put a slab of metal in here, where there is zero electric field inside the metal, it's exactly the same as just putting the plates closer together. In this case, we say we're going to shorten the semester by 4 weeks by just lopping off the last 4 weeks. In this case, we say we're going to make the semester shorter by 4 weeks by putting a 4-week break in the middle of the semester and forcing you to sit on a beach and forcing you to not study. Same result, right? Same result. Okay. Now, let's hook up the battery and do the same 2 races. Again, what matters is what voltage you race through. If I look at this situation here, now it's the voltage between the plates that stays fixed by the battery. And so it's the electron race that's going to be the tie. Okay? Because I'm putting those plates closer together and demanding that the voltage between the plates stay the same, the electric field has to get bigger between the plates. But because this voltage is equal to that voltage, 6 volts, both electrons would be going the same speed after they went through from one plate to the other. On the other hand, when I look at the proton race, now the distance between A and B stays the same, but the electric field is going to be bigger. So I'm going to have a bigger voltage between this A and B. And this proton's going to be going fastest when it gets to B. Now look at it this way. Let's say that's a 12-volt battery. So that means there's 12 volts from here to here. Well, that distance there is less than half the distance between the plates. So that means that this voltage here has to be less than half of 12 by the end equation. This has to be like 5 volts here. If that's 5 volts and that's 7 volts, that gives me 12 volts. But over here, if this is still 12 volts from here to here, well, that's like 2/3 of the distance across. That's got to be like 8 volts from A to B. Does that make sense? Is that making sense?